people used to think that you could create mass from nothing, and that if you did certain things like burn large amounts of mass, you were actually making mass disappear, or you were converting it into energy. Right? Now, these things aren't true, right? The only conversion between mass and energy that occurs is through nuclear reactions, and we have some of that occurring in our power plants, some of it occurring in the Earth itself and on the sun, but this does not occur to a significant level. Well, I mean, depending on your perspective. So, and you never know what kinds of things that you have to emphasize because things change, right? I would have never thought when I was in college that we would be involved with a significant amount of people thinking that the Earth is flat again, right? I thought that we were kind of past that, but you know, different things just pop up. So, and conservation of mass is a law of nature. Conservation of energy is more appropriate because, like we said, theoretically, there is conversion of mass to energy. So, all right. So, another law that I want to introduce to you is called the law of definite proportions. All right? And what this refers to is the handy, convenient, right, fact that when you combine two elements together, let's say I combine hydrogen and oxygen together, right? Then they're going, and I combine them together in a given way, meaning fixed pressure, fixed temperature, whatever. All my conditions are fixed. The combination that I make, whatever it is that I make, will always be the same thing if I repeat that experiment the same way. All right? Now this isn't balanced, like that. These aren't even how you define hydrogen and oxygen. Generally, they're diatomic like that. And I think that's our balanced equation we would generally see. We'll talk about balancing equations at the end of the day today. But the law of definite proportions states that atoms come together in the same way if you treat them the same way over and over and over, right? Now that doesn't mean that we can't have a combination of elements come together and form something different. But if you're going to do this second reaction as opposed to this first one, you have to combine these under different conditions. So the law of definite proportions says that if you combine the same elements the same way under the same conditions, here in Brazil, in Ukraine, wherever you do it, you're going to get the same products. The law of multiple proportion says that if you combine the same elements but in a different way, you might get a different product. Okay? Definite proportions and multiple proportions. So that allows us then to answer questions like this, right? Where we have some information given to us about a chemical reaction. We don't know something about one of the reactants, but we can answer the question. So why don't you guys find a partner, work through this one, all right? See if you can talk to yourselves, or talk to each other and talk through it by yourselves. And then I'll be back in about 85 seconds, and we'll see how far you get, okay? Go try to answer this question. All right, did you get it? All right. So, we have a chemical reaction here where it looks like we're combining magnesium with oxygen to form magnesium oxide, something symbol depicted like this, right? And it says how many grams of magnesium? All right. Grams of magnesium. And we don't know how many grams of oxygen. Whoops, that's supposed to be a question mark. But we know how many grams of product. Therefore, the law of conservation of mass suggests that the difference between this and this has to be from the oxygen. Right? And that's how they began to realize that oxygen was required for combustion. Right? They started doing reactions with metals because as metals burn, they don't result in something like carbon dioxide that's a gas. They result in an oxide that's powder, so it won't go away. And they realized that oxygen was being pulled out of the air, right? They started doing reactions where they didn't have oxygen and they want to burn it off. Yeah?
So, what the heck is this? How are we supposed to assume that if they're making magnesium?
So burns in the presence of oxygen and magnesium oxide was produced, MgO. Yeah. Okay. Any questions about that one? Nice. So, the law of definite proportions, which basically says if I have magnesium oxide here, then the ratio of magnesium and oxygen are the same as if I have magnesium and magnesium oxide over there, or in Kentucky, or wherever, right? If it's magnesium oxide, the ratio of magnesium to oxygen will be the same wherever that sample is. So, talk to your neighbor, see if you can figure this one out. What are they asking here? Wow, you guys talk really quiet.
This is a ratio?
Yeah.
Right. So
The
if
ratio 16.89 to 11.
over 11, right? And then equals 2 over question mark,
Right.
right?
And you remember, you know how to solve that sort of thing? Or?
I think so, yeah.
You got it? That looks good, right? Does that make sense?
Well, they want to go on.
Okay. If you set it in, that like an old math problem?
Yeah.
how you did. They say we have a pile of this magnesium oxide, right? They say we have some magnesium oxide. Here it is. There's the pile of it. And here we have 16.89 grams of magnesium and, whoops, yes, 11.1 grams of oxygen. 11.11 grams of oxygen, right? And then they're saying, what if there was a smaller pile of stuff where we only had 2 grams of magnesium? How many grams of oxygen would that require? Or not require. How many grams of oxygen must be in that sample? Because this is the same material, then there is this relationship, right? The ratio that exists here will exist here as well. True? Thus, we should be able to solve that using math, right? If you've forgotten how that works, 2 over x, we cross multiply, remember that business? So 16.89x equals 11.11 times 2. What's that? 22.22, is that what you said? Divided by 16.89. True? All right. Okay. So, hopefully we got 1.32 grams out of that. Does everybody see how we did that? How did we know that this ratio was the same? Law of definite proportions, right? Good. Any questions about this? Any part of it? All right, wonderful. So, we've had a little bit of discussion already about our atom model. How our model might not be perfect. That's all right. It's a model, and it serves us well, but we don't want to box ourselves in and confine ourselves and pretend like that's the only truth that's out there about the model, right? So, one part of this idea about atoms interacting with each other is that once they interact with each other and form something like this molecule here, H2O, right? You're not going to have scenarios where this H2O in general rearranges and forms something else, right? Our chemicals will generally have a degree of stability, and you can't mess around with the subscripted values in chemicals, right? So, for example, before we get there, I guess, let's talk about this. For example, if I have a chemical equation, like this one up at the top, all right? In this chemical equation, where is there? It's beautiful. In this chemical equation, I've had to put a 2 here to make sure that the number of hydrogens and chlorines was equal to the number of chlorines and hydrogens on this side, right? I changed the number of these things that went in. I didn't put a 2 down here or a 2 down there, right? Because that would change what kind of molecule it is. Okay, so the law of multiple proportions, as I explained, hopefully you gathered it, means that if I combine the same elements, but what? The same elements, but I combine them, what? In different ways, then I might get chemicals or things being produced that have different chemical formulas. Now, when you think of chemistry that occurs where there's no control over the conditions in which the combination occurs. Like this example here, you need sulfur combined with oxygen to form sulfur dioxide, or it can combine with 3 to form sulfur trioxide. Where might you have chemistry occurring, but nobody's really controlling the amount of oxygen that would interact with the sulfur. Right, in nature. Right? So we burn gasoline all the time, and there's no sulfur that we put in the gasoline, but there is contaminants of sulfur in the gasoline, contaminants of nitrogen as well. And those chemicals, when they are oxidized, that's what we're doing when we're burning gasoline, right? We had a conversation about this compound, or no, we had a conversation about the main compound in automobile gasoline. Remember what we decided it was going to be? What's that? Well, I thought we did, maybe we didn't. We talked about automobile gasoline. Octane. Octane was our main component in automobile gasoline. And this is the chemical formula for octane, C8H18. So, in automobiles, we take C8H18, combine it with oxygen, and it produces carbon dioxide and water. All right? That's what happens in your car. That's what makes it go. Okay? But if some of the octane is contaminated with sulfur, then you'll also get either a sulfur dioxide or a sulfur trioxide or something like that. All right? And this becomes a problem because as sulfur oxides interact with moisture in the air, it'll form an acid, like sulfuric acid, sulfurous acid, hydrosulfuric acid. So these are, that's what we call acid rain. You guys heard of acid rain? All right, where chemicals that have oxygen on them, sulfur or nitrogen, combine with water to form acids, and then it rains down on us and causes death. Right? Acid rain used to be like a really big concern. I don't know. What does it cause? What's the major problem with acid rain? Yeah.
Doesn't it just dissolve like limestone or something?
Yeah, it'll dissolve like statues and certain kinds of buildings pretty good. And it does damage rusts, other stuff as well, and it causes corrosion of other stuff as well. Let's see. We've done pretty good in the United States at decreasing the amount of acid rain due to the combustion of fuels. What we generally do is in front here, we try to minimize the amount of contaminated fuel that can get through, right? So factories that burn carbonated materials, like coal is a big problem still because there's still a lot of sulfur that's on coal. But a lot of the factories now are burning natural gas, right? Natural gas. It's a crazy thing. When I was in college, everybody was swearing up and down that we were going to run out of oil one day, and we were going to have to basically take over a Middle Eastern country so that we had energy, right? And people were always concerned. In the 70s, there was this huge scare where there was cut back on how much oil you could buy, how much gasoline you could buy. There were all these lines at the gas station. People thought, this is it. The world's about to end. The place is going to go crazy, right? Not a single soul ever said, well, there's a possibility that in the future the United States will make fuel and export it, right? Even 10 years ago, nobody was saying that. But almost overnight, relatively overnight, in the span of about 5 years, the United States became an energy producing. And they changed the laws because they made the laws that you can't take any export from here, make any export from the United States that is an energy export, because they wanted to make sure it was all here, right? But they changed the laws. They said, yeah, okay, we got so much extra natural gas, let's start letting it go. Right? So, crazy, crazy stuff. The take-home message is, though, that you can get all sorts of chemistry occurring in the atmosphere, lakes, nature, all over the place. And so the law of multiple proportions is free to roam outside of our test tubes, right? Okay, then let's see if we can answer this question. I think that's a little bit too much. We're gonna move on. Let's look at this chemical reaction and make sure we've gathered these words. Reactants. You guys feel like you know what the reactants are? The stuff on the what? Right or left? Left. And on the right, what do we call that stuff? Products. This and all chemical reactions are shorthand for sentences. And that's kind of like a language, right? We have this little language that we utilize because it's just quicker and easier to write it down. But you can always translate it, and your ability to translate it will help you understand what's going on. Okay, we'll work on that as time comes. The arrow here can mean things like yields or reacts to produce. So HCl, 2 HCl, 1 CaCO3, reacts to produce CaCO2, H2O, CO2. All right? This little S means what? Solid, liquid, gas. What about AQ? What does AQ mean? Aqueous, which means it's what? It's dissolved in water. Now, they don't have any other symbol for dissolved in ethanol or dissolved in octane or anything like that, because a lot of chemistry does occur in water, so it's handy to have. Okay, so these are our states of matter. All right, solid, liquid, gas. Aqueous isn't really a state of matter, but it's something we use to express what's going on. All right, so when we want to balance an equation, we can only change the coefficients in front to balance our equation, right? We're not going to be changing these numbers down here, right? Because that changes what? If we change those numbers, we change the what? Change the chemical that we're actually portraying, right? All right, so let's do it. Let's see if you guys can take this equation. First of all, just check and see if it's balanced. Maybe make a list, like different kinds of elements that are in there. Iron on the left, nitrogen, oxygen, hydrogen. And then make the same list, did I forget any? Same list on the right, count them up. We should be pretty good at that. We had a couple of quizzes all about counting atoms and elements, right? So let's find out if this is balanced. If it's not balanced, you're going to change the what? What can you change in here? The coefficients. All right, see if it's balanced. Work with your neighbor. Not balanced, change the coefficients. Good. Go for it. find that as time goes, you don't need to make the list anymore, but for now. Did everybody get to sign the roll?